Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm going to talk about an important topic in physics, namely Galileo's law of falling bodies. You may have heard of this. It was actually Galileo. He was a very famous. He's considered the father of modern science. He was born in Italy. He was Italian. I guess he was born in 1564 and he died in 1642. And he made a science out of physics, really, because before him, it was Aristotle who was kind of the authority on physics. They were just called natural philosophy at the time, and it turned out he was wrong. I mean, he thought that heavier objects fell faster than light objects, and he thought, you know, that was just one mistake he made. He also thought that nature had hard a vacuum, and that would things would fall infinitely fast in a vacuum, and he got it wrong, unfortunately, and unfortunately, the ancient Greeks, and for almost 2,000 years after that, nobody thought of performing any experiments to test his theories, which were wrong. But finally, Galileo did back in the 17th century, early 17th century, and I don't know if he really dropped two rocks from the top of the Tower of Pisa. That's what a lot of people said he did. I think that story is apocryphal, but he did know that in the absence of air resistance, that heavy objects and light objects would fall at the same speed. And I think other people have dropped rocks off the Leaning Tower, and they have almost the same speed if you do this. I just don't think that Galileo did this, but regardless, he did discover the law of falling bodies. And so, what does the law say? Well, it's a mathematical law, and pretty much all of science, especially physics, is really math is the key to understanding physics. So these are mathematical laws, and I guess I have to explain them to you, but they're not that hard. I mean, so here's what you're supposed to imagine. Imagine you're throwing an object like a ball up in the air with an initial speed u. U is just the initial velocity of the ball, and it's straight upward. So you throw a ball up in the air with initial speed u, and then there's gravity, which Galileo discovered is an acceleration. The effect of the Earth's gravity is to accelerate all motion downward, um, and that's due to the gravitational force of the Earth. Newton actually cleaned up this theory, but for now, it's enough to know that there's this constant little g. It's about 9.8 meters per second squared, or in English units, about 32 feet per second squared. It's just how the acceleration of falling objects and in the absence of wind resistance. Wind resistance actually makes things fall. Acceleration, it gets less and less because then there's wind resistance, which eventually cancels out the force of gravity. Like any skydiver knows this. If you jump out of an airplane, initially you're going to be accelerating at 9.8 meters per second squared, but you achieve what's called um, I guess what is it called, terminal velocity, terminal speed, which is about 120 miles an hour. If you're falling at 120 miles an hour, the wind resistance pretty much matches the force of gravity, so you won't fall any faster than that. But that's pretty damn fast. I mean, I've never skydived, but I imagine that it must be pretty painful when you open up the parachute and all of a sudden the parachute opens and you're slowed down almost instantaneously. I don't know what that's like. I don't think I want to try to find out. But anyway, neglecting air resistance is a constant acceleration, and these equations on top just tell you what happens to your speed and your height and the three equations here. So let me just go through them all. If you want the speed or the velocity of your falling or rising as a function of time, equation one tells you that. And you're supposed to imagine this is velocity is actually speed and direction. And if it's in a straight line up or down, there's only really two directions that a falling object can go. It either go up or go down. So you're supposed to imagine in this example, u is positive. So you're supposed to imagine that u is your initial speed, but every second your speed slows down by gt. After 1 second, your speed is going to be u minus g. So imagine you throw a ball up at 10 meters per 20 meters per second, say, and let's just round g to 10 meters per second squared. It's pretty close to that. So after 1 second, your speed's going to slow down to 10 meters per second, still upwards. But then after 2 seconds, it's going to slow down to zero because now t is 2, so g times t is 20. So you're going to 20 minus 20, which is 0. That means that the ball is going to achieve its maximum height after 2 seconds if its initial speed is 20 meters per second, which is pretty fast. Um, and then it's going to start falling down after that. So after 3 seconds, it's going to be falling downwards at 10 meters per second. Finally, after 4 seconds, it's gonna fall down to the ground. It's gonna have the same speed it had when you threw it up, but in the opposite direction. And so now it's gonna be falling down at 20 meters per second, which is pretty fast. So you better get out of the way. You probably don't want to get hit by it. Um, and that's what happens. And that's the speed, the velocity as a function of time. But then there's another equation. Equation two tells you the height of the ball as a function of time. And you can get this by integrating, but you don't have to know about calculus. Integration comes from calculus. So you can actually derive equation two from equation one if you know calculus. You just integrate with respect to time. But even if you didn't know that, there's other ways to derive this formula. And what this is telling you how high the ball is as a function of time. So if your initial height was zero, which is I think what this equation assumes here. So if you plug in 0 for t, you're going to get 0 for h. That means that you've thrown the ball up from the ground. You're probably going to throw it up exactly from the ground. You're probably going to throw it up from a few feet. You can throw it up from whatever you want. You could even throw it up from a balcony of an apartment. It could be 100 feet in the air. But just for simplicity, let's assume that you're throwing the ball up from the ground. Then, so actually, like I said, after its initial height, which is after t equals 0, is going to be 0. But then, say after 1 second, again, let's imagine that you're throwing a ball up at 10 meters per second, and g is 10 meters per second squared. So then you plug in 1 for t, you're going to get let's use the example before that u is 20. So you're going to get 20 times 1, that's 20, minus 1/2 times 10 times 1, which is 5. So after 1 second, it's going to actually be 15 feet high, or 15 meters high. If there was no gravity, it'd be 20 meters high, because it would just go constantly at 20 meters per second. The gravity is slowing it down. So gravity has slowed it down so that it's only 15 meters high after 1 second rather than 20. And then after 2 seconds, that's when I said it achieves maximum height. Let's see what happens. So you're going to get 20 times 2, that's 40, minus 1/2 times 10 times 4. Well, half times 4 is 2, so that's going to be 20. So it's going to be 40 minus 20, 20. So that's its maximum height, 20 meters. That's pretty high. That's about 66 feet, I think. So you've thrown the ball fast enough so that it achieves a maximum height of 66 feet. That's pretty fast. I mean, I think it's kind of hard to throw a ball that high in the air. Of course, you're also supposed to assume there's no air resistance, which makes it easier to throw at that height. And then and then you can do this for t equals 3, t equals 4. You're not going to bother with that. But if you plug in 4, you're going to get 0 again. You could just check that yourself. And for t equals 3, I think you can get 15 meters. This is symmetric, by the way. This formula for t is actually it's called a quadratic equation, and the graph of that is a parabola. I'll get more into that later. But then there's a third equation. What if you just want to know the velocity as a function of height? So say you want to know how fast the ball is moving when it's 10 meters up. Well, then you can use formula for 3 for that. This is a more complicated formula. It involves v squared, but I think I can still do this calculation. So again, u is 20, so u squared is going to be 400. 400 minus 2 times 10, that's 20, times, what did I say, 10 meters. So then you're going to get 200. So 400 minus 200 is 200. You take the square root, that's about 14. So what equation 3 is telling you is then the ball is 10 meters up in the air, whether it's going up or going down, its speed is going to be 14 meters per second. Kind of neat. So I think these three equations pretty much tell you everything you need to know about the motion of the ball. But that's just if it's going straight up or straight down. That's not really all that interesting. I mean, it is interesting, but to make things even more interesting, you can consider the case where it's not going straight up or straight down. Say it's a soccer ball and you're kicking a soccer ball or something, or football. It's going to move in an arc trajectory. That arc is actually a parabola. I mentioned parabolas earlier, but these equations become a little more complicated when you include a horizontal motion, but not that much more. I mean, the formulas for the y component of the velocity are still the same as they were before. It's just instead of the total velocity, you have to use Vy naught, which is the initial y component of the velocity. So if you're only interested in the y component of the velocity of a ball, even if it's not going straight up or down, you basically get the same equations you did for the case where it is going straight up or down. The only complication here is that you also have an x component, and the x component is actually very easy. In the x direction, the velocity stays the same. And that's because there's no force, there's no horizontal force acting on the ball. Even though there's the vertical force of gravity, there's no horizontal force acting on the ball, which means that it just moves in the horizontal direction, in the x direction, if you like, at constant speed, which is all this equation says. You take the initial value of x and you just add vx times t. Vx is the horizontal component of the velocity of the ball, and t is time. And if you combine these two equations, you get a parabola. This slide is a lot more complicated, and don't bother, trying to understand all the formulas here. But this is kind of just a pictorial representation of the previous slide. If you combine the x components and the y components of the motion of the ball, you get a nice parabola, which is what this graph is showing here. And if you want to get a formula in terms of theta, that's the initial angle at which the ball is kicked, then you get these more complicated equations. But you don't really have to worry about that. I mean, and notice that u, I guess they call the total velocity u here, or maybe that's the initial velocity. It's a vector, and you can think of the x component of u is constant because there's no force acting in the x direction, but the y component of u gets smaller. It's just like what I was showing earlier for the ball thrown straight up in the air. It's acted on by gravity, which means that it decreases and eventually gets to zero. That's the height of the projectile of the ball. And you can calculate the height the same way I did when I was showing it being launched straight up, when you just consider the y component. And then it starts arcing down, and then eventually it hits the ground. And you might wonder what's the angle you should kick the ball to get it to go as far as possible. Well, if there's no air resistance, it's exactly 45 degrees. That's pretty easy to prove. Um, if there is air resistance, I think it's a little less than that. I think they tell football players to kick a ball at a 43-degree angle because that takes into account air resistance. But anyway, so that's projectile motion due to gravity, and that pretty much sums up everything there is to know about Galileo's law of falling bodies. But it's not the end of the story. Actually, this is a nice picture too. This is just another picture of projectile motion when you kick a ball, and this one has more vectors in it, so I guess you can kind of see a little better what's going on. But yeah, like I said, it's not the end of the story because for one thing, the Earth isn't flat. I mean, Columbus, I think they say he was the first to show that he wasn't, but we've known the Earth isn't flat ever since the Renaissance, I guess, and because it's not flat, that means that if you could kick a ball fast enough, if your initial velocity was large enough, you could actually go into orbit. And I think this is a really nice picture because this one picture kind of shows what's going on. I mean, the ball goes farther and farther the faster you kick it. Or don't even think of kicking a ball. Think of launching a satellite, which is kind of like kicking a ball. So imagine you had a really high tower here. This kind of looks like the Eiffel Tower in Paris. But yeah, imagine that you're kind of launching. I think you can think of a cannon. That's a pretty good example. So imagine that you're shooting a cannon off the top of the Eiffel Tower in a straight horizontal direction. Well, depending on the speed, the initial speed V0 that you launch at, that you shoot the cannons off, it's going to go a certain distance before it hits the ground, and you could actually use Galileo's law of falling bodies to approximately that how far it goes, for small speeds. But then as the speed gets larger and larger, since the Earth is round, it actually goes farther than you expect because the Earth is curving away from where the cannon would have landed otherwise. And if you launch it fast enough, eventually it'll go into orbit. I mean, it looks like they show five projectile motions here. The fourth one, it just barely grazes the surface of the Earth. It looks like it lands, in near Asia somewhere. But if it did a little faster, it'll actually go into orbit, and in the absence of any air resistance, if it's in space, it'll just keep going in orbit. And that's how satellites work. Satellites are just projectiles with a fast enough speed that they can stay in orbit around the Earth. But one thing that a lot of confuses a lot of people. I mean, if you were, say you were an astronaut and you were in one of these satellites orbiting the Earth, you would feel weightless. And you might think there's no gravity because you feel weightless. That's not true. You're falling. If you're in orbit around the Earth, especially if you're close to the Earth, you're falling just as fast as you would be falling if you were going straight down. It's just that you're falling in a circle, which is a weird thing to imagine. But there's centripetal force of the Earth acting on you. It's actually the centripetal force that's due to gravity that's keeping you in orbit. So it's not true. I mean, it's true that you're weightless, but that's just because you're in a frame of reference in which the satellite is accelerating the same rate you are. But you're still accelerating and you're going really, really fast. I mean, you have to be going fast enough so the centripetal force is strong enough to keep you in orbit. And that's very fast for orbiting around the Earth. It's about, 8 kilometers per second, or about, I think in English units is about 17,000 miles an hour. Very, very fast. And I have one more slide to show you. You can actually go even faster. This is kind of the same thing I was showing in the last slide. Here they actually do show a cannon. So there's actually five projectiles they show in this diagram. A is when it's going pretty slow, when it just hits the Earth not too far from where you launched it. So it's basically following Galileo's law, falling bodies, and then you do it a little faster, you get to B, and now you can kind of see the Earth curving away. And then to C is where I showed you last time. That's where it goes in orbit, circular motion. But it doesn't have to be circular. If you do it a little faster, you get an ellipse. You get an ellipse where I guess the place where you launched it from becomes I think it's called the aphelion. That's the point in the orbit where it's closest to the center of the Earth. And then the point on the opposite direction is called the perihelion. That's where it gets farthest from the Earth. So its initial speed is going to be greater than its uh, orbital speed. So it'll be greater than 17,000 miles an hour, maybe closer to 20,000 up where the cannon is. It'll do that. And it can go even faster. And notice E. E actually escapes. So there's an escape velocity for the cannonball. For the Earth, it's about 25,000 miles an hour, or about what in metric about 13 kilometers per second. Very, very fast. And actually, the astronauts had to do this when they went to the moon. The only way you could get to the moon is to escape the. You have to go at least the escape velocity because you have to escape being orbiting the Earth, which is exactly what the astronauts did. So they actually went 25,000 miles an hour on their way to the moon. Pretty damn fast, you know. And I think that's the fastest anybody's gone, even to this day. So, um, maybe some satellites, some of the satellites like Pioneer and Voyager, they probably went faster than that because they had to escape the sun as well. So they had to go even faster. But the fastest any human has ever gone is about 25,000 miles an hour, or 40,000 kilometers an hour, which is the escape velocity of the Earth. So anyway, that's my video on Galileo's law of falling bodies. I hope you enjoyed it, and I'll see you next time.